Okay, so we want to try implicit differentiation with partials, basically. Okay, so they said if e to the xy plus sine of x times z plus y is 0, what's the partial of z with respect to y? You just do this the exact same way you do implicit differentiation in Calc 1, right? Hit the whole thing with a partial with respect to y, and then see if you can isolate the partial of z with respect to y that pops out, right? So I'm literally just going to take this whole equation, hit it with a partial with respect to y. So I've got e to the xy plus sine of xz plus y is going to be, what do you get on the other side?
0.
Yeah, the partial of 0 with respect to y is going to be 0, right? All right, which of these pieces are going to be easy? Uh-oh. Why is sine xz easy?
Constant.
Yeah, there's
No y, right? If there's no y, the z's derivative with respect to y should be 0, right? But that's going to cause me some major issues, right? Namely what? What am I assuming by saying that z is constant with respect to y? That there's not any change, specifically that the partial of z with respect to y is 0. You guys see that that's an assumption I'm making? If I look at z and I think to myself, maybe z is a function of x and y, right? Or at least a relationship of x and y. Maybe it fails the vertical line test, but it's somehow related. You guys remember this trick from implicit in Calc 1? Right, you're hitting everything with a ddx operator in Calc 1, and then you'd like to say, well, the derivative of y with respect to x is 0, except that the point was that you couldn't assume that. So here, I'm going to get, out of this piece, I'm going to assume that x is constant with respect to y, but I'm going to assume that z is a function of x and y, so that it has a partial.
And that's where you get your dz dy?
Yeah, and that's where I get a dz dy. So here, when I differentiate this piece, I'm going to get some other stuff too.
dz dy cosine xz.
So I'll get cosine xz
X
times
dz dy
partial of z with respect to y.
times x.
That's from the...
Z.
No, that's from the chain rule.
Yeah.
And I've lost a piece here, right? Yeah, I lost an x in there. Oops, and I also lost... So that was this piece, right? Turned into this stuff. So I got the derivative of the outside, right? Cosine. Times the, or at the inside, times the derivative of the inside. X was constant, so I left it alone, and then z depended on y. Okay, so this is really me looking at this and thinking, okay, z is a function of x and y. X is just not, right? X is independent, and y is independent. That's cool, Okay, what about the other pieces here? So I got...
Y just is 1.
So you're going to have 1 plus 1, and then x
X e to xy.
x e to the xy. Perfect. Plus this stuff.
And now you just isolate variables again here.
Yeah, now I want this piece by itself, right? So I'm going to subtract
X e to the
1
xy
and x
plus
e to
1.
the xy. So I'm going to get cosine of xz times x times the partial of z with respect to y is negative 1 minus x e to the xy.
So divide by cosine xz times x.
Perfect. So we'll divide by x cos xz. And so in the end here we'll get the partial of z with respect to y is
Negative 1 minus x e to the xy divided by cosine xz times x.
Don't we have a Z still?
Ah, we still have a Z, right?
Yeah.
You guys see that? You remember that happened in Calc 1's implicit differentiation too?
Mhm.
Yeah. That's okay.
Oh yeah, we do.
Yeah, the reason I can't get rid of that, right, is that this is an implicit derivative. This thing probably fails the vertical line test, right? And so there are 2 points here, right? Or maybe 3, or maybe infinitely many anyway, right?
Well, it's a family of functions instead of just one.
This is definitely...
Or for the differential.
Oh, this thing? Yeah, this should be a family of slope lines, right?
Yeah.
One for each level at which the vertical line passes through. Right? You guys all see that? So this is saying the change in z with respect to y depends, right, on both the x and y, right, where you are, but also the height you're at. Probably because this thing fails the vertical line test and there's a few heights, right? And then the y change could be different at each of those heights. Does that kind of make sense? The thing you might use this for that kind of idea, would be something like, here's a sphere, right? I want to find a tangent plane someplace, maybe above an xy point, right? But there's 2 points kind of above that, right? There's one above and one below. There's 2 tangent planes there, right? There's one up here and one kind of down here. You guys see that? So the slope of that tangent plane is going to depend on which side I'm on. That's kind of what's going on here, but of course this is a little bit messier surface.